Okay, definitions of laser intensities. When we talk about laser intensities, we probably need to separate into three different cases. For clarity, let me define E of t as the electric field divided by a constant square root of 2 eta. Eta is the wave impedance, 377 ohms in vacuum. Okay? So E of t is no longer field, but field divided by this constant. Okay? But at least they are, at least E of t is proportional to electric field, although not equal to electric field. Then, if we talk about the narrowband pulses, which is the bandwidth much smaller than the carrier frequency, as we defined earlier, then there are three cases. First, instantaneous intensity. Instantaneous intensity is defined by factor of 2 times E squared of t. And if you use the carrier envelope representation of E of t defined earlier, instantaneous frequency is governed by this formula. And if you plot the instantaneous intensity against the time, you can get something like the blue curve. Okay? So what does this mean? It means if you have a detector with infinite bandwidth, okay, fast enough, and if you use it to detect the optical field, then you can get a trace like the blue curve, oscillating very, very fast. Okay, how fast is the curve? The detector has to be at least twice faster than the carrier frequency. Then you can get this. Okay, but you know, so far we don't have a detector like this. Okay, so it's just imaginary case. Instantaneous intensity. The second case is the envelope intensity, which is small a absolute square. It's a function of time represented by the red solid curve here. And the meaning is for each optical cycle, you have up and down, right? If you take the average value, you point position by position, you got the red curve. Okay? So that means if your detector is not fast enough to trace the fringes, but fast enough to trace the envelope, you got the red curve. Okay? And the third case is average intensity. If your detector is too slow, it cannot trace the envelope function still, then you get a constant, which is the average height of the red curve. And it's the so-called average intensity. So there are three different intensities: instantaneous one, envelope one, and average one. The first two are functions of time. The third one is a constant. Okay? Let's think about what do we have in reality now. Think about the photodetector and the oscilloscope you can purchase commercially. Which one can we directly measure? We can only measure average intensity, because even the red one is too fast for our photodetector and oscilloscope. Right? So it's a big problem. If you want to know the temporal waveform of your femtosecond pulse, photodetector and oscilloscope is not a good choice. Okay. So we have to spend some effort in that technical problem, right? But at least you know, conceptually, if your photodetector is infinitely fast, you can get the blue curve. If it is in the order of maybe 10 femtosecond, maybe you can get the red one. But so far, all you can do is the average. Okay. Okay, any question? Because of the square. Cosine square theta is 1 plus cosine 2 theta over 2 theta, right? The frequency is double. Field and the intensity, because of the square relation, intensity oscillate twice fast. Right. Oh, this vector? Okay. Because the red curve is the average of the blue curve. Say if your peak is here, your value is almost 0, right? Your average is 1. So it's a 2-to-1 relation. So if the formula about envelope intensity is a factor of 1, then the formula about instantaneous intensity need a factor of 2. Okay. Of course, you can define there is 1 here, but now you need 1 over 2 here. Either way should be okay. Envelope 就是我们刚刚谈的嘛，就是我们在谈它的表达法的时候有讲，我用 carrier envelope representation 表示 electric field， 我有一个 complex envelope function A of t，A of t 的意义就是这个东西。你有一个 short pulse， 电场其实很复杂，但是包络可能不太复杂。我讲的包络就是这个包络。那我们通常关心的就是这个包络的形状。It's a Gaussian profile, or it's a triangular profile, or it's a square profile. We need to know. Besides, we probably need to know the fringe density variation. Is it a constant, or it's a function of time? In the future, we will know if it's constant, it's a transform limited pulse. If it's a function of time, it's a chirp pulse. Okay, and some physical systems respond to transform limited pulses and chirp pulse differently. So you need to know the fringe density variation. So combining together, you need to know the complex A of t function. Okay. And if you know them, then you can know the envelope intensity, the red curve here. Very few systems is fast enough to respond to the fringes. Okay. Of course, there are systems fast enough. Could be, as we discussed earlier, could be the electronic motion in an atom. It's very fast. But otherwise, these fringes don't matter. Your molecular system might respond to the red curve only. So we do not have to care about the fringes. Yes. OK， 好，我用中文说哈，基本上这个是2:1的关系，这可以吗？因为这个在震荡的时候，红色的就是蓝色取平均值，蓝色是每一瞬间都有高忽低的值，对不对？但是你从 peak 到 valley 再回到 peak roughly 叫一个 cycle。我在这个 cycle 里面取了 average， 然后一个 cycle 取 average， 取完就变成红色的。那红色的会在哪里？大致上就是极大跟极小值的平均嘛。那极小值一定是0啊，那极大值要是2，平均后才会是1嘛。所以我说蓝色的峰值跟红色大致有2:1的关系，所以这个2，这个1，或者这个1/1也可以。原因在这里。Any other question? Okay. So the last topic of this lesson is the impact of phases on pulse formation. Let me show you 3 examples. Example 1 is you have big N modes. N could be a large number, like 1,000. Okay? So your bandwidth is about big N times mode spacing, delta omega, as I mentioned before. And if we assume all of them have the same magnitude, E0, so you can see the height of each delta function is the same. And we also assume the phases are 0 for all of them. So they are in-phased longitudinal modes. Okay? Then what will happen in the time domain? This is the representation in the frequency domain, right? What is the synthesized waveform? Remember, each delta function here represents a sinusoidal function in the time domain. But depending on the position of the delta, the oscillation periods are different. Like to the right-hand side, you have higher frequency, you have shorter period, right? A delta function to the left-hand side corresponds to a sinusoidal function of greater period. Okay? But all of them share the same amplitude and the same phase. So let me show you 3 specific cases. Say we pick up the central 3 modes for illustration. The red one is the leftmost mode, right? Corresponds to the lowest frequency. So represented by a red sinusoidal function. The period is largest. The green one is in the middle, so the frequency is a little bit higher, represented by the green sinusoidal function with shorter period. And the blue one is the rightmost mode, corresponding to highest frequency sinusoidal function. And remember, these 3 modes share the common amplitude, so these 3 curves have the same amplitude. And they have 0 phases, so all of them are cosine functions. Peak occurs at t equals 0, right? Then what's the result if you superpose these sinusoids together? You can expect constructive interference around t equals 0, right? Because all of them are cosine functions. All of them are maximized at t equals 0. So if you observe t equals 0, you got peak always. And the summation is very big, right? But other than the t equals 0, the origin, what happens? If you shift the observation instant to the right a little bit, you can see red, green, and blue curves drop differently. And maybe these are just 3 of the big N modes. There are more, right? Maybe some of the other sinusoids will see negative values. So you have positive, you have negative. If you sum them together, you will get essentially 0. Right? So only t equals 0, you have constructive interference. Other than that, you might have 0, always. So you have a short pulse, right? That's the result in the time domain. You got short pulse. And quantitatively, the peak intensity is about n squared of I0. I0 is the peak intensity due to a single mode, E0 squared. Okay? So if you sum big N modes together and they are in phase, your peak intensity will increase not by a factor of big N, but by a factor of big N squared. A large enhancement occurs. Okay? And if you check the pulse width, delta t, it's about TR over big N, which means the repetition period is TR over the number of modes. The larger number of superposed modes, the shorter the synthesized pulse width, if they are in phase. Okay? So peak intensity increased by a factor of n squared, and the pulse width is reduced by a factor of big N. So the larger the mode numbers, you got stronger and the shorter pulses. Okay? But this is the perfect case. Phase locking. All the phases are the same. If we check the second example, all the modes still share the common magnitude, E0, but the phases are divided into two groups. It can be 0 degree or 180 degrees, just two possibilities. Say we assume the left-hand side, the left half modes are phase equals 0. The right half phases are pi. Then you have, you still pick up the central three modes for illustration. The red and the green delta functions correspond to cosine functions in the time domain. But the blue mode corresponds to a minus cosine function in the time domain because of the pi phase shift, right? Then what is the superposition? You cannot have the shortest pulse. This is the result. Quantitatively, the peak intensity is only 50% of the best case, the previous case. So the height is not as tall as the previous one. And the pulse width also increases by a factor of 2 compared with the best case. Okay? So roughly speaking, both peak intensity and the pulse duration degrade by a factor of 2 if you have two groups of phases. If you have only one group of phases, like the previous case, you got the best. And if you can divide the phases into two groups, you degrade by a factor of 2. Okay? Lastly, another extreme case. If all the amplitudes are still the same, but the phases are random sequence, okay? What would happen? For example, the red one, green one, and the blue one have 2 pi over 3 phase, minus pi over 2, and 0, respectively. Just 3 random examples. Then the superposition should give you something like this, the noise-like waveform. Okay? This time, you have pulse duration, nothing but the repetition period. Peak intensity is similar to the average intensity. So peak intensity and the pulse duration degrade by big N times. Because now all the big N modes have randomly different phases, or divided into big N groups of phases. So the degradation factor is big N. So in this case, superposition of a lot of modes do not contribute to pulse generation. And this is the case of the sunlight, right? Sunlight is white light. It means a lot of frequencies simultaneously exist, but you have no show pulse. If you measure the sunlight, you should get something like this, a noise-like waveform. So what does the broad bandwidth contribute in this case? It only contributes to the short correlation time. It's not the pulse duration. Correlation time is the width of each noise-like peak. The broader the bandwidth, the narrower each noise-like peak could be. But overall, there is no clear pulse at all. Okay, so you have to tell the difference between the correlation time and the pulse width. Okay. Any question? So the last 3 pages again emphasize the importance of phases in pulse formation. You need broad bandwidth. It's very clear, but you also need equalize all the phases together such that you can have short pulse in the time domain. And usually, it's not so easy to do that. Locking the phases of a lot of very different frequencies is uneasy. Okay. Sorry, we have finished lesson 1. Can you answer these questions? Let me show you one example. How to measure molecular dynamics by pump probe scheme. Do you still remember the pump probe? You have a short pulse, divide it into 2 arms. The stronger one is the pump pulse, hits the test sample, kicking out the mechanism, like the stopwatch, t equals 0, right? Then the weaker probe pulse comes in at a later time, which is controllable by your delay line. And you can measure the probe pulse spectrum. The spectrum tells you the molecular oscillation or rotation mode, right? Because the absorption peak will give you the information. Then you monitor the spectrum as a function of delay, you know the dynamics. Okay? Second question, what is gain saturation? Good, small signal gain. Without lacing, you have small signal gain. Wow, you remember the numbers, so it's amazing. Okay, qualitatively is enough. Gain saturation means whenever you get coherent photons out, you have to pay the price. The number of excited state electrons is reduced. So your gain is reduced. And this behavior means gain saturation. Okay, just qualitative descriptions. Okay, so I encourage you to ask yourself these questions. If you can answer all of them, that means lesson 1 is okay for you. Okay, we have only maybe 5 minutes. Let me briefly introduce lesson 2, active mode locking. This is the first technique to generate short pulse to be covered in this subject. It's divided into 3 parts, starting with the easier approach, Gaussian pulse analysis. Then the more complicated approach, coupled rate equations and the steady-state solutions. Just some basic idea. The conventional CW lasers, you have a single mode in steady state, right? In the frequency domain, you have a single delta. You have constant envelope intensity in the time domain, okay? So this is the picture we have seen in lesson 1. Then, to generate short pulse, one of the possibilities is adding an extra cavity modulator. Okay, so this is the traditional CW laser, and if you place an intensity modulator outside the cavity. Do you know what is intensity modulator? If you drive the modulator with a periodic signal, the transmittance of this piece of material will change periodically. Okay, so if you have constant output power after the modulation, what do you have? You have something like this, right? Very easy. But the question is how short the pulse width you can get in this way. Right. It's totally up to the speed of the modulator. If the width is 1 picosecond, it's 1 picosecond. And usually, we do not have 1 picosecond modulator. Maybe we have only tens of gigahertz modulator or tens of picosecond modulator. So this technique only gives you pulses with tens of picosecond or even broken pulses. Never femtosecond pulse at all, right? But if you change the scheme into this one, still using intensity modulator, but this time put it inside the cavity. What would be the result? The answer is you can get very, very short pulse. But why is that? Okay. So now we have an intensity modulator inside the cavity, and we drive it with a periodic signal with frequency Fm, which is 1 over Tm. Tm is the modulation period. Okay? And then this is the picture. It's the transmission curve of the modulator. Its driving signal is periodic, so transmission is periodic. And peak-to-peak spacing is Tm, modulation period. The other one is the pulse trend in steady state. The peak-to-peak spacing is repetition period, TR. How to determine TR? As we studied in lesson 1, TR depends on the cavity. Okay? And the Tm depends on the modulator driving signal. So essentially, they could be different. Okay? But if you purposely make TR equals Tm, equalize these two parameters, maybe you can get this. See the pulse peak sees transmission peak. Your pulse wings see less transmission. Together, it means the pulse peak is preserved, while the pulse wings are cut short. right? Then the tendency is you compress the pulse in the time domain in the presence of the modulation curve, right? Although the modulation is pretty weak per round trip. Think about the modulation here, okay? You can shorten the pulse, but the force should not be too strong. But now, the modulator is inside the cavity. That is the key point. Although the pulse shortening effect is pretty weak per round trip, but it circulates inside the cavity many, many times, right? So the pulse shortening effect can be essentially amplified. Then you got very short pulse in steady state. Okay? And what is the steady state? The pulse cannot be even shorter anymore. The pulse shortening effect is counterbalanced by other effects that will broaden the pulse. Okay? But we need mathematical analysis to take this into account. In this figure, if you only consider the modulator, you only consider the pulse shortening effect. But if you consider the gain medium, which is necessary for any laser, you will see pulse broadening effect as well. And in the presence of two counteracting forces, as I mentioned before, some balance has to be reached. Then you have steady state. Okay. So without any quantitative analysis, maybe you can quickly catch the point how to generate short pulse by inserting an intensity modulator inside the cavity.